Hey everybody, Professor Briner here again. Today we're going to be talking about Chapter 11, Factorial Designs. So you may remember me saying before that a factor is just another word for an independent variable. So factorial designs are what happen when we look at two independent variables at once. So I'm going to be doing 3 mini lectures for this. You're going to get, the first one is going to be an introduction to factorial designs. The next one will be about something called main effects and interactions. And then the third mini lecture will be about different types of factorial designs. So let's start out by thinking about what we mean here, a factorial design. So an experiment, the way we've normally been thinking about it, holds everything constant except for the one independent variable that a researcher is investigating. So that might be looking at gender differences, might be looking at males and females. It might be looking at an experiment, a classical experimental condition and a control condition. Or it might be like what we did with Data Project 3. It might be looking at one independent variable with 3 levels. So we had our young people, our adults, and our older adults in the Data Project 3. So 3 levels, but still one independent variable. Now, sometimes it's good to just look at one independent variable at a time. It makes for a very clean study, but these variables rarely exist in isolation, right? We find that there's one effect in a lab, but if we get out there in the real world, then we have a situation where, well, now that variable is interacting with a lot of other things, and it might start to get a little tricky. Think about the relationship between caffeine and alcohol. So we know that caffeine speeds you up. If you drink a coffee, you're going to be more alert than if you didn't drink a coffee. And we know that alcohol tends to slow you down. So if you drink alcohol, you're going to be slower than you would be if you hadn't drank alcohol. But what happens when you combine the two? We know that there are a lot of alcoholic drinks that have caffeine in them. Think about a rum and coke, think about an Irish coffee, think about any of those drinks that have both alcohol and caffeine. So what happens when you give somebody one drug that speeds them up and another one that slows them down? So if we want to know how caffeine and alcohol combine, we have to do a factorial study. So when we think about these factorial studies, it might be useful to sort of plot them out on a grid like this. We could have one condition that's our caffeine condition, or let's say it's our independent variable rather than our condition. So we have one independent variable, that's caffeine. In this example, we have 3 levels of the independent variable of caffeine. Some people get no caffeine, some people get 200 milligrams, some people get 400 milligrams. Now for alcohol, that's our second independent variable, so we can put it on the other axis of the grid. And for alcohol, in this example, we only have 2 examples, or 2 conditions, or two levels rather. 2 levels of alcohol, alcohol or no alcohol. So that means we have 6 different conditions altogether. So we have 3 levels of one independent variable times 2 levels of the other independent variable, and that gives us 6 conditions. One condition where they get alcohol but no caffeine. A baseline condition where they're getting no alcohol and no caffeine whatsoever. Now we have a condition where they're getting 200 milligrams of caffeine but no alcohol. In this condition right here, they're getting alcohol and the 200 milligram dose. Over here in the top right, they're getting both caffeine and alcohol. They're getting 400 milligrams of caffeine. And over here, they're getting 400 milligrams of caffeine with no alcohol. So that gives us 6 conditions altogether. Let's see what that looks like when we plot it out. Well, here are our reaction times for those conditions. Let's say that we take the people in each one of these conditions and we give them whatever level of alcohol or caffeine is specified, and then we put them through a task where we are measuring their reaction time in milliseconds. So you see 210 milliseconds right here. That means about 2/10 of a second. There's 1,000 milliseconds in a second. So now we can start to see what the effects of caffeine are and what the effects of alcohol are. So the value in each cell is the relationship in each condition. So the reaction time for each condition, this is for no caffeine and alcohol versus no alcohol, no caffeine. Notice the reaction time is lower when they have no caffeine and no alcohol compared to when they're getting alcohol alone. That makes sense, right? That our people who are getting alcohol are going slower than our baseline condition, our baseline of no alcohol and no caffeine. Now let's look over here. These are the people who are getting 200 milligrams of caffeine. The alcohol group is about 50 milliseconds slower than the no alcohol group. Okay, so our alcohol group is still slower, but notice that gap has lessened. Here there's an 80-point difference between our alcohol and our no alcohol group when no caffeine is involved. But when you give them 200 milligrams of caffeine, that difference is only 50 milliseconds. So let's see what's going on here in the 400 milligram condition. Well, we're still seeing that if you get alcohol, you're going to be slower than if you got no alcohol. But once again, the gap has narrowed. Now there's only 20 points separating our no alcohol and our alcohol condition when you get 400 milligrams of caffeine. Now another way we could think of doing this is we could sum across conditions. So no caffeine, we could take an average of what people are doing in the alcohol and the no alcohol condition and say that when you consider both conditions together, overall, people who get no caffeine have a reaction time of about 250 milliseconds. We could do the same thing over here. We could say when you average 250 and 200, so in other words, we're looking at what the 200 milligram caffeine condition does regardless of alcohol. Well, 250 plus 200, that's 450 divided by 2, gives us a mean of 225. So notice, when you're not considering alcohol at all, we still see a decrease in reaction time when you get caffeine. Now let's look over here at 400 milligrams of caffeine. We can average across these two to look at the effect of 400 milligrams of caffeine regardless of alcohol. So 210 plus 190 is 400, divided by 2 is 200. So when we don't take alcohol into account, we see that caffeine speeds you up the more of it you get. You get no caffeine, you're at 250. 200 milligrams of caffeine speeds you up some more, and 400 speeds you up even more than that. Now, we can do the same thing in the alcohol conditions. We can look at the effect of alcohol regardless of caffeine, and we can look at the effect of no alcohol regardless of caffeine. So if we summed across these conditions and divided by 3, we'd get an overall mean of 250. If we summed across the no alcohol conditions and divided by 3, we get an overall mean of 200. In other words, we see that regardless of caffeine, alcohol slows you down. 50 milliseconds slower here than here. Remember, lower numbers are faster, higher numbers are slower. So regardless of caffeine, alcohol slows you down. Regardless of alcohol, caffeine speeds you up. But what do they do in combination? I think it's the size of the difference here that we need to pay attention to. How that gap shrinks the more caffeine you get. Let's see what that looks like graphically. Okay, here we have on our x-axis our caffeine conditions. Our baseline, no caffeine, 200 milligrams of caffeine, and 400 milligrams of caffeine. And we have reaction time in milliseconds here on our y-axis. Remember, lower is faster. This is our plot for the no alcohol condition, the people who had no alcohol in their system when they got the caffeine. And here is the plot for our alcohol condition. These are the people who got alcohol or no alcohol plus some caffeine. So let's take a look at what we see here. These two dots that I'm going between, that's the difference between alcohol and no alcohol when no caffeine is in your system. Here we have the difference between alcohol and no alcohol when you've got 200 milligrams of caffeine. And here we see the difference between alcohol and no alcohol when you have 400 milligrams of caffeine. So notice what's happening here. Overall, both conditions speed up the more caffeine they get. We can tell that because both of them have a downward trending slope. And we can tell that across all the caffeine conditions, you're slower with alcohol than without. Notice that gap that always exists. It might narrow, but the gap always exists between alcohol and no alcohol. So, in other words, the effect of alcohol depends on how much caffeine you have in your system. The effect of caffeine depends on how much alcohol you have in your system. That's kind of the heart of the factorial design, showing that what one independent variable does has an effect on what another independent variable does. So another way to think of this, in a traditional experiment, one independent variable is one factor. The independent variable of age, the independent variable of gender, the independent variable of caffeine, or the independent variable of alcohol. When you have two or more factors, in other words, two or more independent variables, you are doing a factorial design. So often, it's referred to by the number of its factors. In our example, we've got a two-factor design. We have the factor of caffeine, and we have the factor of alcohol. So this is a two-factor design. Sometimes we denote the factors by a letter, so we could say alcohol is factor A, we could say caffeine is factor B. If we threw something else in there, that would be factor C. And let me go over how to notate factorial designs for you. So you'll often see factorial designs notated like this, like a 3x2 or a 2x2 or a 2x4. Here's what it means. So the number of integers you have tells you the number of factors. So 3x2, we have two integers, the integer 3 and the integer 2. So we know we have two independent variables. Now the value of the levels, in other words, what the number itself, the value of the number, tells you how many levels of the independent variable there are. Here it's 3 because there are three levels of the independent variable. And here it's 2 because there are 2 levels of the independent variable. So what that means, we've got caffeine, it has 3 levels, and alcohol that has 2 levels. So 2 independent variables, one has 3 levels, the other has 2 levels, and that's why it's a 3x2 design. You can envision that when we look at that grid, right? Our grid is also 3x2, 3 levels of caffeine, 2 levels of alcohol, for a total of 6 conditions. Remember, 3 times 2 is 6. Okay, that's all I wanted to cover in this mini lecture. On the next one, we'll talk about something called main effects, which are the effect of any independent variable on its own, and interactions. And that's what independent variables do combined with each other. So that's what we'll cover next time.